Today, we're going to be talking about solving more exponential equations. And in today's lesson, we're going to be using two really important properties to help us solve a problem like this. So, in yesterday's lesson, we talked about either having the same base on both sides of the equation or rewriting as the same base on both sides of the equation. So we'll look at this example in a little bit, but we're going to talk about the change of base property, and we're also going to be talking about the inverse property to help us solve an equation like this one. So the change of base property is going to show up a lot in today's examples and in the practice. And basically what the change of base property does is it allows us to change a log with a base of any number into a log with a base of 10, which is what our calculators generally work in. So we talked about evaluating logarithms a couple weeks ago using properties that would allow us to rewrite in exponential form and then kind of evaluate from there. But there's going to be some logarithms that we won't be able to use that method for. So this is where the change of base property is really helpful. So let's look at an example. So let's try to evaluate log base 4 of 13. So before, what we were doing was we were saying, okay, well, what if I took this log base 4 of 13 and I set it equal to some variable? Then I was asking myself, well, what could I raise 4 to get a 13? Well, if we think about what we can raise 4 to the first is 4, so that doesn't work. 4 to the second is 16, and we've already exceeded 13. So basically what this is saying is that we can't evaluate log base 4 of 13 by hand because this process doesn't work here. So the change of base property says we can take the log of whatever the number is next to the base, and we can divide it by the log of the base. So the way that this problem over here would be set up would be the log of the number next to the base, so that would be the log of 13, divided by the log of the base, and our base here is 4. So we're going to divide that by log of 4. And then our calculator can help us actually do this. So in my calculator, I would type in log of 13 divided by log of 4. I would just be careful that I would want to close the set of parentheses around the 13 before I hit the division button. And I want to round this to 3 decimal places. And that's just going to be kind of our rule of thumb here for these problems. So my calculator is telling me that this is approximately 1.850. And this isn't an exact number because your calculator is going to give you a lot more decimal places than that. So this is why I'm just putting the approximate. And this is, again, not an exact answer. So when we go to use this in our equations, our equation answers are going to be a little bit off since we are rounding these numbers. So let's look at one more problem. So let's evaluate log base 7 of 20. So I'm going to first rewrite this as the log of the number next to the base, so log of 20, divided by the log of the base, so log of 7. And an easy way to remember the change of base formula is think about the base. Base means bottom. So when I want to do the change of base formula, the base goes on the bottom of the fraction. So my calculator, when I evaluate log of 20 divided by log of 7, is telling me that this is about 1.5395. And I know that I want to round to 3 decimal places. So since there's a 9 here, I'm actually going to be rounding this number up. So I'm going to say that this is actually to 3 places about 1.540. And this will come up in pretty much every problem that we're going to be doing today. There's going to be a couple of exceptions. The change of base property, just to kind of go back to this note up here, we do not need to use this for equations with e to the x, and we'll talk about that in a little bit. So just kind of keep that in mind. The other special property that we're going to be using to solve today is called the inverse property. And this is kind of a combination of a special property that we talked about when evaluating logs, as well as the power property that you saw on Friday. So basically, the inverse property basically says that if I have a log base a of a raised to some exponent, this whole expression just gets evaluated to whatever is in the exponent. And then we can also talk about the natural log because these will definitely come up today too as well. We talked about the special property that the ln and the e always undo each other. So when I have an ln and an e to an exponent, this whole expression just gets evaluated to whatever's in the exponent. So let's look at a couple of examples before we go on to actually solving some equations. So log base 4 of 4. We talked about this as being a special logarithm a couple weeks ago. Anytime you have this base here matching this number here, our rule said that this just gets evaluated to 1. And it doesn't have to have a log of a base of 4. It could be log base 3 of 3, log base 7 of 7, log base 9 of 9. As long as these two numbers match, it's going to be 1. And that works here because technically the exponent on this 4 over on the right-hand side here is 1. So using our inverse property, log base 4 of 4 to the first, 1 is in the exponent. This just gets evaluated to that exponent of 1. Kind of similar, except now we're just working with a variable. Log base 7 of 7. Again, this base is matching this number, is just going to evaluate to whatever's in the exponent. So since the exponent is just an x here, that means that log base 7 of 7 to the x is just x. Similarly, log base 2 of 2 to the x plus 1. Again, this base of 2 is matching this number 2 here. It doesn't matter that there's stuff in the exponent. This is just going to be evaluated to whatever is in the exponent. So log base 2 of 2 to the x plus 1 just gets evaluated to x plus 1. So moving on to some natural logs, because those are also going to come up today. Ln of e to the 7x minus 2, we're going to use this inverse property here. Ln of e to the x is equal to x. So ln and e, again, these undo each other, to the exponent of 7x minus 2 actually just gets evaluated to 7x minus 2, since that's just the stuff that's in the exponent there. So now let's look at some equations that we can actually apply these two properties to. So let's go back to that 2 to the x is equal to 15. So we were talking before about how we could manipulate one or two sides of the equation to get the base to be the same on both sides. Well, let's see if that'll work here. So I have 2 to the x equal to 15. So I want to know, is it possible to rewrite 15 with a base of 2? Well, let's see. 2 to the first is 2, so that doesn't work. 2 squared is 4, so that doesn't work because that's not 15. 2 cubed is 8, so that doesn't work. 2 to the fourth is 16. So I've already actually gone over this number of 15. So it's actually not possible to rewrite this problem like we were doing in yesterday's practice. So instead, we have to think about, well, how can I undo this base of 2 to get the exponent by itself? Well, that's where our inverse property comes in. So basically, I want to identify what the base is first. So that's going to be kind of my first step here, and I'll just kind of star that up here. Because once I identify the base, it's going to be very easy for me to decide what I need to do after that. So my base here is 2. So in order to use the inverse property, I'm going to undo that base of 2. So that's going to tell me that on both sides, because whatever I do to one side, I have to do to the other, I'm going to take the log of whatever the base was that I identified. So in this case, it's 2. So log base 2, and then I'm going to bring this expression down of 2 to the x is equal to, and again, since I took log base 2 of the left-hand side, I also have to do exactly the same thing on the right-hand side. So I'm going to also take log base 2, but instead of taking it of 2 to the x, I'm going to take it to whatever is on that side of the equation. So log base 2 of 15. So this is where the inverse property actually comes in, because now I have log base 2 of 2. This number here matches this number here. So this side of the equation is actually just going to be evaluated to whatever's in the exponent. And in our exponent is just x. So log base 2 of x, or 2 to the x, is just x. And over here, I'm left with log base 2 of 15. And now that I have some base to some number, this is where I have to actually use the change of base formula. And again, that's going to tell me to rewrite this as x equals the log of whatever the number is next to the base, so log of 15, divided by log of 2. And again, that base is 2, so when I'm using the change of base formula, log of 2 should be in the bottom. And my calculator is going to tell me that this is approximately, again, I'm just dividing log of 15 divided by log of 2, is approximately, and I'm going to round to 3 decimal places, 3.907. And the nice thing about these equations is you can always check them. So I'm going to go ahead and I'm going to do a check step here. So my x value is about 3.907. I'm going to go back to my original equation up here. 2 to the x is equal to 15. So basically what I want to check is if I plug in the x value that I just got of 3.907, does it equal 15? So let's see, 2.3 or 2 to the 3.907. And I'm going to plug that into my calculator. But the problem here is we rounded our change of base, this log of 15 divided by log of 2, to just 3 decimal places. So when I go to do the check step, it's going to be off a little bit. So 2 to the 3.907 is actually about 15.001, which is a little bit different than 15, but it's pretty close. So if you get something that's pretty close, I'd say that that's probably pretty accurate. All right, so let's see what happens when the base isn't 2, because it doesn't always have to be. So what happens if we have an equation with 5 to the x is equal to 35? Well, again, I need to identify my base. Here, my base is 5. So to undo, to make that inverse property work here, I'm going to take, instead of log base 2, I'm going to take log base 5 of 5 to the x. Because again, my base is 5, so I want to take a base of 5 here. And whatever I do to one side, I do have to do to the other. So log base 5 of 35. And again, here's my inverse property happening on the left-hand side. This number here matches this number here. So this stuff on the left-hand side using the inverse property just evaluates to whatever's in the exponent, which is just x. I'm left over here with log base 5 of 35. And here, this is where I need to use the change of base. And I'm going to just abbreviate that to COB, change of base, because I need to be able to evaluate this. And again, my calculator doesn't work in bases of 5, it works in bases of 10. So to rewrite this with the change of base, I'm going to take the log of the number next to the base, so 35, and I'm going to divide it by the log of the base, so log of 5, which is approximately, when I use my calculator, 2.209. And again, I'm just using my rule of thumb here of rounding to 3 decimal places. So I'm just going to do a quick check here just to see if that seems reasonable. So my original equation was 5 to the x is equal to 35. So when I plug in this x value of 2.209, 5 to the 2.209, I'm just going to check to see if it's close to 35. Again, it's not going to be exact because we rounded this number. So it's about 34.997, which is pretty close to 35. So seems reasonable. All right, let's look at something that's a little bit different. So now we're identifying our base to be an e. So I have an e to the x is equal to 72. So this one is different than the last two examples because when you have a base of e, remember that the operation that undoes the base of e is the natural log, or that ln. So here, my undoing process is going to look a little bit different than the last two problems. So to undo an e, I need to take the natural log of both sides instead of taking a log of some number base of both sides. So what that's going to look like here is I'm going to have ln of e to the x. And again, whatever I do to one side, I do have to do to the other. So I'm going to take the ln of 72. And here is actually my inverse property right here. ln and e next to each other undo. So I'm just left with whatever's in the exponent. So the exponent is just x here. And that's equal to ln of 72. And my calculator can actually do this calculation. I actually find that the E problems are easier than the other problems because the calculator just does this stuff without having to worry about the change of base formula. So in my calculator, I would just hit the ln button and then type in 72 and hit enter. So here our x value is approximately 4.277. And again, I can go ahead and check to see if this answer is going to seem reasonable. So I'm going to go ahead and do a check step here as well. So my original equation was e to the x is equal to 72. I'll go ahead and plug in my x value that I just got. So e to the 4.277. When I plug that into my calculator, it's about 72.024. So again, we're a little bit off, but we're pretty close. So seems reasonable. All right, so those were pretty basic types of exponential equations. What happens if there's other stuff around the base? So here we've got some stuff going on with subtraction and multiplication, and then same thing over here. So we'll look at a couple of these types of examples. So the key to these types of examples, when you see that there are other mathematical operations going on around the base, you have to get the base by itself first. So that's going to be your first step. Get rid of anything that is around the base. So the first thing that I'm going to undo in this problem is I want to undo this -5. So I'm going to add 5 to both sides of my equation. So that's going to leave me with 4 times 3 to the x is equal to 52. And be very careful at this point. It is going to be really tempting to want to multiply this 4 and this 3 to the x, but you can't. To undo, to get rid of this 4, you actually have to divide it on both sides. So I'm going to get rid of that by dividing. So divide each side by 4. That's going to leave me with 3 to the x is equal to 13. And now this is a pretty basic equation. This is pretty similar to examples 3 and 4 that we just did. So I'm identifying my base. Here my base is 3. So to undo the base, I have to take log base 3 of both sides. So log base 3 of 3 to the x, and whatever I do to one side, I do have to do to the other. So I'm also going to take log base 3 of the right-hand side, so 13. Here is my inverse property. This 3 and this 3 match. So that I'm going to be left with whatever is in the exponent, which is just an x, is equal to log base 3 of 13. And this is where my change of base is going to come in. My COB, change of base. So to rewrite this so that I can evaluate, I'm going to say x is equal to log of the number next to the base, so log of 13, divided by the log of the base. So here my base is 3. So log of 13 divided by log of 3 is approximately 2.335. And I'm also going to do a quick check on this one. And my check is going to be a little bit more complicated because I have more stuff going on up here, but you can still always check your answers. So I'm going to take my 2.335 and I'm going to go ahead and plug it back into my original function up here. So 4 times 3 to the 2.335 minus 5. And I actually just plugged this into my calculator exactly the way that it looks here. And my calculator told me that it was about 47.016, which our original equation had just 47 here. But again, this rounding down here is going to make our answer a little bit off. But 47.016 is pretty close. So check, that works. All right, let's look at one with a base of e with a couple more steps. So here's my base. My base is e. I want to get it by itself, so I need to undo this -7. I have to undo the 2. So I'll do the 7 first. So add that to both sides. That will leave me with 2 times e to the 2x is equal to 15 plus 7 is 22. Then I need to undo this by division. Get rid of that 2 by dividing it out on both sides. So I'm left with e to the 2x is equal to 11. So at this point, I've gotten my base by itself. I've isolated that base. So my base here is E. And to undo an E, remember that its inverse operation is an ln, or natural log. So I'm going to take the ln of e to the 2x. Whatever I do to one side, I also have to do the other. So I'm going to take the ln of 11 on the right-hand side. Again, here's my inverse operation going on here. ln and e undo each other. So I'm left just taking down whatever's in the exponent. And in this case, I've got two terms in the exponent, or I've got two numbers here. So 2x is going to come down, and that's going to be equal to ln of 11. And if you want to, you can evaluate the ln of 11 at this point. I'm just going to do this all in one step. So I know that I need to get rid of the x. And since this is an ln, I don't have to worry about the change of base formula. So I'm going to go ahead and divide each side by 2. But when I do this, just be careful. Make sure that when you're typing this in, if you have like a TI-83 or a TI-84, you are closing the parentheses around the 11 before you type in the division by 2. Otherwise, it will definitely throw your answer off. So ln of 11 divided by 2, that's telling me my x value is approximately 1.199. And I'm also going to go ahead and do a quick little check step here. So I'll do my check over here. So I'm going to plug this x value back into my original function up here. So 2 times e to the 2 times 1.199 minus 7. And again, I just used my calculator and I just plugged this in all in one step. And my calculator is telling me that's approximately 15.002. So again, it's not exactly 15, but it's pretty close. So 15.002 seems pretty reasonable. All right, 2 more examples, and these are kind of a little bit more complicated than the ones that we just looked at. So now we want to solve 7 to the x plus 2 plus 3 is equal to 75. So the goal here is always going to be the same in our first starting steps. Get the base by itself. So here's my base. That's the term that's got the exponent. So I have to get rid of this 3 first. So I'm going to go ahead and subtract that. So that will leave me with 7 to the x plus 2 is equal to 72. And even though we've got a couple things going on up here in the exponent, I've isolated my base. So at this point, I have to ask myself, okay, what is going to undo a base of 7? Well, my inverse property says to take log base 7 on both sides. So log base 7 of 7 to the x plus 2 is equal to log base 7 of 72. And again, here's my inverse property. This number here matches this number here. So I'm going to go ahead and evaluate and bring down whatever's in the exponent. So set log base 7 of 7 to the x plus 2 is actually just evaluated to x plus 2. And that's going to be equal to log base 7 of 72. And at this point, I need to go ahead and use my change of base. I know I have stuff going on over here, but I'll deal with that after. So I'm just going to rewrite x plus 2, and I'm going to go ahead and do my change of base here. So log of 72 divided by log of 7. And I'm going to take one step to actually evaluate. Log base or log of 72 divided by log of 7 is about 2.198. And the reason I'm not writing it to the right here is because I still have stuff on the other side that I have to deal with. So log of 72 divided by log of 7 is approximately 2.198. And now I can go ahead and actually solve for x here. So my last step before I'm done is to go ahead and subtract that 2 out. So that tells me that my x value is about 0.198. And I'm going to go ahead and I'm also going to go ahead and do the check step here. So my check, I'm going to go back up to the original equation, and I'm going to plug in this 0.198. So 7 to the 0.198 plus 2, and then plus 3 down below. I'm just going to clean this up a little bit. So that's going to give me an exponent of 2.198 plus 3. And my calculator is telling me when I go ahead and evaluate this 7 to the 2.198 and then add 3 to it, it's about 75.032. which in my original equation was just 75 up here. But again, since I did round some stuff in here, it's not going to be exact, but it should be pretty close. So 75.032 is pretty close to 75. So seems reasonable. All right, let's look at one more problem, then you'll do some practice on your own. So now I've got some more stuff going on over here. But my base, the term with the exponent, is 3. So I need to undo the stuff around it to get that base of 3 by itself. So first thing I'm going to do, get rid of that minus 3 by adding it to both sides. So that will leave me with 2 times 3 to the 2x plus 1 is equal to 16. And again, I know it's going to be really tempting to want to turn into a 6 over here, but don't. You want to go ahead and divide that. So get rid of the 2 by division. And you're left with 3 to the 2x plus 1 is equal to 8. And at this point, you've isolated your base. You've gotten that 3 by itself. So then you have to undo it. So to undo it, I'm going to go ahead and take log base 3 of both sides. So log base 3 of 3 to the 2x plus 1 is going to be equal to log base 3 of 8. And at this point, this number here matches this number here. We're going to use the inverse property. So I'm going to bring down whatever's in the exponent. So in this case, it's going to be a 2x plus 1. And then we're left with a log base 3 of 8 on the right-hand side. Here's my change of base. It's going to be pretty similar to the last problem. At this point, I'm going to rewrite this right-hand side as a change of base. I'm going to keep the left-hand side just as 2x plus 1. So 2x plus 1 equal to log of 8 divided by log of 3. And I'm going to evaluate this side similar to what I did in the last problem before I do anything with the left-hand side. So I'm just going to keep on bringing down that 2x plus 1. And log of 8 divided by log of 3 is about 1.893. And now I can start undoing this stuff over here to get the x by itself. So first thing I'm going to do, subtract 1. So 2x is equal to 0.893. And then I'll go ahead and divide each side by 2. So that's going to tell me that my x value is approximately 0.4465. I know for the other ones I've rounded to 3 decimal places, but my calculator is giving me 4 decimal places on that one, so I'm just going to kind of keep it as it is right now. So now I'm going to see, well, does this answer seem reasonable? So I'm going to go ahead and check it. So my original equation had a lot of stuff going on here, so I just have to be careful about how I'm going to be plugging this in. So 2 times 3 raised to the 2 times 0.4465 plus 1 minus 3. And I'm just going to simplify this exponent a little bit before I evaluate, just to make sure I'm not making any silly algebra errors. So 2 times 0.4465 plus 1 is about 1.893. 893 minus 3 in my calculator. Oops. When I evaluate that, tells me that this is approximately 13.004, which again, in our original equation, was telling us was equal to 13, but since we did some rounding, it's going to be a little bit off, but that seems reasonable. So now it is your turn to do some practice. Please let us know if you have any questions.